Hello everybody, welcome to class today. 302, video 6. I've like something in my eye. Cleaning it. Okay, I think it's gone. So, alright. So, we are live, I hope. Yeah, 18 viewers. Great, awesome. So, today is going to be the last day of talking a little bit about recurrence relations, and we're going to start into a new topic. We're going to talk about linked lists and arrays very briefly, actually, and maybe even we'll talk about sorting today, but I don't know. That's kind of ambitious, so we will see. So, so far, here we go. So far, you know, with the recurrence relations, we have sort of had two approaches to them, you know. Both of them involve a certain level of guesswork because at the end of the day, when we're trying to come up with that sort of general case, you know, we're kind of trying to deduct it. We prove by induction. We also did a sort of build and expand methods and sort of working our way from the end or the beginning, ultimately trying to find the pattern. And once we have the pattern, then we just have to prove that the pattern is correct, essentially, right? So that's kind of the heart of recurrence relations. However, it's a very painstaking process, and sometimes you can't avoid it. Just flat out, I'm telling you, you cannot avoid it, okay? However, for a large amount of recurrence relations, there is a shortcut that you can use, and that is known as the Master Theorem. I will post a link to the Wikipedia on it later. In fact, actually, I can post that on here. Master Theorem. Yeah, perfect. That one. I will also post it on the comments if you're looking on YouTube. And so the Master Theorem is basically a shortcut to solving some recurrence relations. And it's not the kind of shortcut that just like solves all problems and you're good to go and everything. But for a large range of them, you can just plug it in and then it'll tell you the solution to the recurrence relation. That's pretty cool, right? So, you know, they're going to talk more about it in detail in Analysis of Algorithms 477. So I'm not going to go too into detail, and I am going to cut some corners. I'm trying to mostly just show you how it works so you can actually use it and benefit from it. But we'll skip a lot of the theory as to the why it even works and a lot of the special cases that because the Master Theorem is kind of a coverall for a lot of different sort of shortcuts. In fact, if you go on Wikipedia, you can see that the article is pretty big and they have example of admissible and inadmissible equations, and I'll talk a little bit about some of those. And they have different cases and all these things. We're really only going to look at a tiny piece of that. So if you want to see more, you can go on Wikipedia, you can Google it, or you can just wait until you take 477 and then they talk about it. So yeah, that's kind of what we'll do. So first of all, so I can save some time, I'm going to go ahead and I took a picture of my notes, so I'm going to just paste that here so you can see it. So which one should I do first? Let me see. Do I have the other one? No, I don't have the other one. I only have this one. So okay. So let me write some stuff first and then paste it. So first, let me go ahead and okay. No, I'll paste this one. I think I can paste this one. There we go. Copy, paste. So we're only looking at part of what the Master Theorem can do. There we go. Perfect. So I wonder what that was in the background, like what that book was. I will never know. So, okay, there we go. You guys can read that. Perfect. So this is the part of the Master Theorem that I want to look at because this is the one that's most useful to us, okay? So the Master Theorem says first of all, you got to create the recurrence relation, okay? There's no shortcut there. So you have to look at code, and if it's recursive code, you have to come up with the recurrence relation. And how do you do that? Well, you convert the code into an easier form of recursion potentially, and then you know, you see it. You know, if there's 2 recursive calls, then you put a 2 in front of the t, right? If there's 3, then you put 3. You know, there's like some people were asking me with the assignment, when you have, you know, 2 nested loops, how do you do that? You just put a 2 or a 3 next to the t, right? So essentially that kind of covers you for the number of recursions you have. It's pretty simple as that. But anyways, you come up with the recurrence relation, okay? In fact, let us look at the recurrence relation that we solved last class. So that was T of n. In fact, here, I probably just copy it. It was, here we go. T of n is equal to 2t. Ooh, don't move that. Copy it before I mess it up. There we go. I should be able to lock part of a file. That would be a nice thing. What's that? Oh, that's a picture. There we go. Okay, weird things are happening. It's getting glitchy on me. So, okay, so T of n, I don't know where the B and N came from. I think maybe it got copied from above. Take the watch off. Let me just make sure I did not erase something by accident here. Ah, it was from build solution. Okay. So, yeah. So T of n is equal to 2t. And then T of n, the 2t part inside is n divided by 2 plus 4n. And you got your base case, okay? And so, this recurrence relation is actually perfect for the Master Theorem, because the Master Theorem expects you to submit a recurrence relation that's sort of split into I would say maybe 3 components, okay? So the first component, you know, first of all, you got to make it T of n is equal to whatever. And then the first component is you have your function, right? You have your t function. And so that's the recurrence relation itself. That's basically the next case, right? And that recurrence relation has to be in the form of t and then n divided by something. Now that something could be 1, so you could just make it n. Like you could make it 2n, 3n, or whatever. But the point is that you have to make that b into a real number, okay? Similarly, you have the a on that side. That a, it could be 2, 3, 4, whatever, but it has to be a number, a real number again, okay? And finally, you have the plus theta n to the power of d, okay? That's a little bit tricky, and I'm going to hand wave a lot, and I'm going to say that what that means is whatever you have there, you have to convert it to an asymptotic complexity of its own, and then format it in that form, okay? So this will make sense as I run an example. As you can see, there's some limitations on what A, B, and D can be. They all have to be positive. A has to be greater than 0, but not 0. That does not work. In fact, if it was 0, there would be no recursion at all, actually, because that would be, the t term would be 0. So yeah, there would be no recursion. So yeah, B has to be more than 1. So that is because you don't want to A divide by 0, and B, you can't have a negative number in there, okay? 3, or D in this case, has to be greater than or equal to 0, okay? So it can't be 0. So you might not even have that term at all, okay? It might be just a constant there. So in the format, in a problem like the one that we have here, you know, we look at what this is. In fact, here, let me just rewrite that piece down here. So T of n is equal to AT n over b plus theta and d, okay? So we have that and we have this. I hope that it's clear and obvious as to the A, because that one is just easy. That's just a 2 right there. So what we're trying to do is we're trying to first figure out if this will apply with this Master Theorem case. And if it does, let's identify what A, B, and D are going to be, okay? So A is going to be 2, because as you can see, it's a perfect match, okay? B is similar. B is also a perfect match because, here, let me highlight it with a different color. This B matches this 2 right here, okay? That's also very clean cut. The one that's a little bit tricky is this one. So you got your theta n to the power of d, okay? That one has to match this. But how do we make that actually work? okay, what you do is you do what I showed you on like the first day when we were talking about certificates and whether something belonged to an asymptotic complexity of a certain class, okay? So what you want to do is you want to convert 4n into whatever the O of n would be, okay? Whatever that asymptotic complexity would be. And you want it to be as tight as possible, because remember, technically speaking, 4 of n belongs to any asymptotic complexity that's basically bigger than that, right? So I could say like O of n belongs to n cubed. I could say it belongs to n squared or even n factorial, right? But that's kind of bad because I'm basically selling my algorithm short, right? I want it to be as tight bound as possible, which means that I want it to basically be O of n, right? And how is that the case? Well, you could show with your certificate that C in this case would be 4 and n will be greater than 1, right? And that would show that 4n belongs to n, right? So we already did that. So you're basically going to do that kind of thing here. You're going to convert whatever the piece of the formula that you have there into the asymptotic complexity belongs. Now here we've been talking about big O, and here you see theta. So that's where I'm going to hand wave a little bit because again, they'll talk about it in a future class. Just think of it as if it was big O there and convert the 4 of n into whatever the big O would be. In this case, as you can see, it would be O of n, okay? So once you do that, just, I guess, put a theta instead, again, hand waving that part. And so now it's a lot easier to see how this actually matches this one up here, right? So this one and this one, how they match. Now you can see that this is just n to the first power. And so d would be equal to 1, okay? So that's the part that we're doing a little bit of hand waving because it turns out that there's a little bit more to it than that. You have to read the Wikipedia article for that and find out more. But again, this is kind of like a bonus topic, okay? It's only meant to help make your life easier without really knowing the intricacies of how this works, which you should know, but it's beyond the scope of this course, okay? So we figured out what A, B, and D are. Now what? Well, the Master Theorem has a couple of cases that you have to figure out which one to pick, and then you're going to get your answer immediately. That's the really cool part, okay? And so the way that you pick the answer between the three of these, so this one, this one, and this one, is you got to look at this comparison right here. You got to take D, and then you got to take the log of B and A, okay? And you got to compare those numbers and see which one's bigger, or if they're equal in the specific case, right? So right now we have A, B, and D. A is 1, A is 2, B is 2, and D is 1, okay? So let's go ahead and for all of these three options that we have here, you can see that we got to take the log of B of A. So let's go ahead and do that. So log base B A, okay? So in that case, damn, I have like hair all over the place. Since B is 2 and A is 2, this is basically doing log 2, 2, right? So 2 to what power is equal to 2? Just 1, okay? So essentially, the answer to that log B of A is just 1, okay? So, now what? Finally got the hair out of my face. Now, let's look at what D is. D is equal to 1, okay? So, D is equal to 1. So now we're going to compare 1 and 1. Is it greater than, is it less than, or is it equal to? Well, in this case, 1 is indeed equal to 1, I hope, right? So in that case, you know, that is going to be this middle case. Case 2. D is equal, oh, Jesus, I have so much hair, like, in my face. It's because I have a fan on because the lights are hot, so it's like blowing stuff into my face. Sorry. But here, D is equal to log B of A, okay? So log B of A is equal to 1 and D is equal to 1. So in this case, because they're equal, we're looking at case 2, okay? In case 2, the answer that we are seeking is right here. So let's go ahead and copy that case 2 beneath right here. So case 2 says, copy it from here, since I can't see it on the same page, it's O n to the power of D log n if D is equal to log B of A. And this is case 2, which is the one that applies to us, right? So in this case, what is d? D is equal to 1, right? So all we're gonna have to do now is just plug that in and we get our answer. So n log n, okay? Power of 1 there essentially, right? So we just get rid of it. And voila, we just got our answer. We spent an entire class period solving this recurrence relation last class, and we just solved it now in like, well, it took about 15 minutes because I explained it, but in reality, it would have taken me like 1 minute from like getting the recurrence relation, looking at my master theorem, you know, computing log b of a. Well, first of all, getting a, b, and d, making sure that they are all okay. A is greater than 0, b is greater than 0, d is greater than or equal to 0, so that's okay. Check log b of a, check d, see that they're equal, put case 2, plug in d into that formula, boom, done. Literally like a minute, okay? Probably takes you longer to write the stuff than to think about it. So, yeah, boom. And is that what we got last time? Let's go ahead and take a look. Here we go. N log n, right here. See that? So, that's it. Can you already appreciate the Master Theorem? Are you guys hyped for the Master Theorem? I hope you are. So, there's a little bit of a catch, though, to the Master Theorem. Now, don't start to get disappointed on me. It's not that bad. But the only catch is this. When you're solving a recurrence relation, you get the exact answer for that exact problem. So, like, in this case, we got that the exact answer was actually 4n log n plus 4n, right? So, what you see right here. These are the exact answers. I mean, I kind of told you that, you know, 4n is basically the same thing as n for all intents and purposes because it's a constant. Just like it, you know, if you have something of n cubed plus n, the n is insignificant compared to the n cubed, right? So 99.9% of the time we don't care about that. That 1% of the time that we do care is I guess if you're really trying to show that your algorithm is better than somebody else's, and it comes down to the point where, like, because here's the thing, theoretically speaking, n log n is the fastest that you can do a sort. And I'll explain that when we get to sorting, but probably next week, I suppose. But even if we get to about that, we won't talk about that piece. And so it turns out that, like, that's the best, right? So if that's the best, if somebody has n log n with a factor of 2 in front of it, and then somebody has with a factor of 4, in theory, the people with the factor of 2 are slightly faster than the one with a factor of 4, right? So the constant doesn't matter in the big picture, but sometimes when you're doing that picture close finish, I think they call it, then it kind of matters, okay? So in those scenarios, having the exact answer can be useful, okay? But outside of those very rare scenarios, you don't care about that. You just want to see that it's n log n. That's kind of it, okay? And so recurrence relations will get you the exact answer. Master Theorem, on the other hand, will not do that. Master Theorem will just get you that generic answer. It'll tell you n log n, which again applies for pretty much 99% of the cases. And so in the test, you are okay with using the Master Theorem, unless I ask you for like a specific case, which I think I might. One of the questions I do and one of them I don't. Depends. At least that's what I did last time. So essentially, it's in your benefit to know the Master Theorem because it saves you time and it makes your life easy. So let's go ahead and do a couple of other examples with the Master Theorem just so you can get a grasp for it. And also we can see the usage in the other two cases. So for example, let's do the one for I think it was the first example that we did for these stuff. Like the one that was like t of n minus 1 or something. We'll get there eventually. I think this one right here. Okay, I think this is yep, that's the one we solved. So this one. T of n is equal to t of n minus 1 plus 2. Okay, this one's gonna cause us some issues, I think. All right, so this is the one that we are looking at. Can we solve one of the questions from the homework? We could, if you tell me one of the recurrence relations from that. I don't know. I don't remember that. I think this would be it. Like this would be an example of that. That would be like a generic for loop. This one. But if you have a specific one, just tell me tell me which one it is at least, so I can open it here on the the PDF. Syllabus teaching assignments. So assignment 2, right? PDF. All right, I have the PDF open. So now you gotta tell me which one you want to see. Code 1, 2, 3, 4, I suppose. Maybe 4 is the hardest one. So yes, I will. Oh, code 4. Yeah, 4. Okay. All right. So we'll do that one next. Let's do this one first since I have it here, but I have it already open. I can't see because of that. Also, everything is dark now. There we go. Let there be light. Okay. So we got this one. Can we apply it to the Master Theorem? Okay. So here we have just a bit of an issue because we have that -1. So how do we handle that -1 there? Okay. If you look in this format, A would be equal to 1 because there's nothing next to it. So you can just say it's a 1 there. The theta ND would be basically equal to 0 for D because n to the power of 0 would be just 1 all the time, which is kind of matching what we have here. We have a 2, but whatever. It's close enough. And then the problem is the n divided by b part, okay? N divided by b has to be greater than 1, okay? In this case, we're not dividing this. So this is actually a scenario where it wouldn't work in the Master Theorem because it can't be formatted that way. However, typically, something of this system like this is pretty easy to solve without it. So because as you saw, we just basically expanded it and canceled all the terms out, okay? But this one's one that we can't use, so no good for the Master Theorem. So as you can see, not everything can be good for it. Now, looking at the one from the homework, the code from the homework is for I is equal to 0, I is less than n times n I plus plus. So that's the outer loop. And then we have 2 more loops, essentially. Same thing. J equal to 0, j less than n, j plus plus, and then finally k. K is less than 3 times n, k plus plus. Okay? And then pretty much nothing happened inside, but whatever. Okay, so that's pretty much the full code. So what we first need to do is we need to figure out what the asymptotic complexity of each of the loops is, okay? And so it doesn't matter which one we start with, but I think it's a better thing to just start from the inside out. Although again, it really doesn't matter because we're gonna combine them later on. So let me pick it up in color so we don't get confused. And so the way we're gonna figure this one out is we're gonna see this right here, this part of the loop, the middle term. That is going to tell us how many times this has to run before it stops. It's running one at a time because it's k++, but it needs to run until it gets bigger than that. So it's going to run 3n times. Okay. Next, we're looking at the second loop here. This second loop, we got to make sure that this loop and this loop are not interacting. That's very important because otherwise things get complicated. Here they're not. Because this loop is independent of the other loop, really. And they're all independent of each other. So in this scenario, that second for loop is only running from 0 to n. So that's just going to be n then. The one out here is actually running n squared times because of the I. The I is going from 0 all the way until n times n. So this one's going to run n squared times, okay? So basically now we have the 3 loops. We have n squared, we have n, and we have 3n. Now here's the thing. If these loops were one after the other, then I would just add the terms together like this. However, the loops are not one after each other. They're actually nested. And when they're nested, you have to multiply them together. So actually it's going to be n squared times n times 3n. So the actual solution to this would be n cubed n fourth 3. Okay, so that's just algebra. All right, so that asymptotic complexity would belong to the class of O of n to the fourth. The certificate to that would be that c has to be equal to 3 and n has to be greater than 1. Okay, so that will be the iterative version of this. Now, how do we make this recursive? Well, there's two ways of doing this. One way is to flatten the loop into essentially just one big loop and then do that. That's an easier way because that's going to give us a recurrence relation of a much simpler form. Or alternatively, you could have written 3 functions and essentially function 1 calls function B and function B calls function C, and then that's basically your recursion. That's a lot harder because you're going to have a 3 term associated to that, okay? So how do you unflatten a loop? Okay, well, sometimes you can do it, not all the time, but in this case it's quite simple because it turns out that, you know, what is happening here is independent of what is happening here, here, or here, right? It's just doing the same thing. So like, I know that in the example code, I just have a semicolon there just to kind of show that, like, you know, it doesn't really matter what's there. You could just written out like a cout statement or something. But if I had a little variable that I said like, you know, int x equals to 0, and in this line of code I said x plus plus, semicolon, like that, then you would find out that if x was, you know, if n was equal to like 10, then x would have the equivalent of 10 squared, sorry, not 10 squared, 3 times 10 to the 4th power. That would be how many times that would probably print out, okay? And you could experimentally test it, and I'm sure you guys did, and got somewhere around that, okay? So, the way that I can unflatten this loop is, I can actually just combine all of the terms into one big loop. So, what I can do is I can write the following code. I can say for I equal to 0, I is less than, leave that blank for now, I plus plus, and the semicolon. So what I need to do here is I just need to throw in all of those terms together. So for sake of actually showing you that that's actually what's happening, I'm going to actually copy paste them, but I could have just manually written them. So first I'm going to copy and paste the first one there. Then I'm going to copy paste the second one, which is just an n. And the way that I'm going to put them together is I'm going to multiply them together. Okay, that's very important. Do not add them together. Multiply them. And finally, the third term, which is at 3n. Okay? I'll have to shrink that one because it's kind of running out of space. Okay? Like that. Now, better way of rewriting this would be, of course, the way that I had it in the green text, which is I is less than oh, did I copy one too many n's? I did. I don't know where this n came from. There we go. Oh, no. I see. No, that was fine. It's because of the other one. So anyways, what I want to copy is the one in green text, which is just 3n to the 4th. So 3 times, and oh, I guess I don't have, I mean, I could call the pow function, but sure, I guess I'll just do it like that. There you go, that's n to the 4th. Okay, so you could do that. So now you have unwinded the loop. And so now you can make your recursion so much easier. I did a recursion relation for each loop and then solve each of those. Is that allowed? Yes, that is allowed as long as you ended up with the final asymptotic complexity that was basically n to the 4th power. If you did get n to the 4th power, you're good. If you didn't, then you're screwed. So yeah, okay, that's good. So anyways, now that we did that, if you're trying to convert this into recursive code, it's very easy once you know that there's just a generic loop. The best thing to do is to convert it into a while loop first. This is going to take a while, pun intended, I guess. But I have a video on it if you're watching 202 for recursion. But essentially what you do is just make it into an infinite loop that's just basically running while true. And then you write an if statement here that is what is in your loop thing there. Also start by declaring a variable, so declare I equal to 0, and then copy and paste the if 3. I'm just going to shorthand and say n to the 4th here, but you know what I mean. Then you put a break statement here, and then that's basically your recursive case. Otherwise you do x++, right? Because it's just whatever we said that we're counting. It doesn't really matter what's there. Okay? Why am I writing ghetto code like this? Because once you do it like this, it's just super obvious how to make it into recursive code. Because now if I call the recursion like let's just call it foo, the function foo, and we pass as a parameter here the value of n and then the value of I, and I suppose we could pass x, but we're not going to do x. We'll just say that it just couts it. Actually, no, let's just do x so it matches. Why not? I could actually have returned that as the return value. I could just return x, but whatever. So then my base case just becomes that same thing. In fact, I'm just going to copy it from here. So I'll put if that, then just return. Otherwise, then just call the function again with n plus I, not I plus plus, because otherwise this thing will go forever. And then also plus x, I suppose. That's why I didn't want to put it, because it's kind of repetitive. But yeah, there's your recursion. And so now that you did this recursively, then you can very easily see that the recurrence relation is just going to be t of n minus 1 plus 1. Because every time that you're doing this, it is just getting one step closer to the goal. Okay? And so, well, not quite, because the n is going to go not until n technically, but until 3 of n minus 4. So not quite that one, because that actually would give us linear time. So this would run t of n is equal to, wait, no, that's correct. That is correct. Because actually the way that I ended up doing this, because it's only one loop like this, it's going to still just run until n. However, n in this case has now become n to the 4th power, like that. So this would actually, this looks like it's going to end in linear time like that, but n is not actually n. N is actually 3n to the 4th. So you can just replace that with that and end up with 3n to the 4th, so then you get the same answer. Yeah. So that's why. If you did it the other way, if you did it with the nested calls, then you could potentially have 3 function calls here, and so then you would actually end up with something that would be like this. T of n is equal to 3t of n, 3t of n or 4t of n? I think it would be 3t of n. Yeah, because you have 3 loops. Yeah, 3t of n. Yeah. Plus 1 probably. So there's different ways of doing this, but as long as you get the right answer, which is this, then you're okay. Okay? So anyways, hopefully that answers your question. 3n to the 4th power. So are we good on that? I hope so. Anyways, going back to the Master Theorem, let's go ahead and do more examples of that. So I have a couple here. Let's see which one we want to do. Kind of wish I would just like post this like that so you could see them. It'd be faster to show you a lot of them. But yeah. Maybe I have them already here. That'd be great. I do. But this one I don't want to show you the answer immediately. No, so we'll do this one from scratch. Okay, so here I have a recurrence relation. The reason I have these pre-prepared is because I wanted to have all 3 cases apply. And so this one's going to obviously be a little bit different. Okay, so there's our recurrence relation. How could we have gotten this recurrence relation? There's the 8 there indicates that like we would have had, instead of having 1 recursive call, we would have had 8 recursive calls inside of 1 function, okay? That is like horrifying to just think about, but we would have had that, okay? So we would have ended up with something like that. Now, could you have unwinded that to just 1 recursive call like we kind of did with the loops? Yes, maybe, but the point is that you ended up with this, okay? Typically, I don't see more than 2 recursive calls and stuff. Like quicksort will have a 2T there because there's 2 of them, but that's kind of it. I don't think there's other algorithms that even go beyond that. But anyways, this is some made up recurrence relation, I suppose. Okay, so in this case, you know, this is our A right here. This is our B. And then this is going to have to be our theta f of, or theta of n, or you can think of it like your function, okay? F of n. And so, how do we convert that into that theta of n format so that we can figure out what D is? Very easily, again, you just basically do your certificate for it. A lot of the times, it seems almost redundant to do this because you kind of got used to it. I mean, this is now going to be C is equal to 1,000, and then n is greater than 1. And essentially, this is going to belong to n squared, right? Okay, so essentially your D is just that. That's usually most of the cases. They're very, very straightforward ones. Because if they weren't, it wouldn't actually work for the Master Theorem. So we got our A, we got our B, and we got our D. So remember, we got to take the log of B of A, right? Make sure, yeah, log B of A. So let's take the log B of A of this. The A is 8 and the B is 2. So that's basically taking that, which is 2 to what power is equal to 8? That's 3. So we end up with the comparison of D, which is equal to 2, right? D is equal to 2 right here. That looks like 25 because of the arrow. Let me clean that up like that. Okay? There you go. So now we are comparing 2 and 3. 3 is bigger than 2, right? So if we go back to the Master Theorem, that is going to be a different case because now they're not equal. That's going to be case 3, right? The log B of A, which is 2, which is 3, is bigger than 2 here. So case 3 is using this format here, which is basically take the log B of A part, which we know was equal to 3, and that's basically the solution, n cubed in this case. So that I can just copy paste. Like such. Okay, so that's case 3. We have if D is greater than log B of A, we know D is equal to 2, or sorry, less than in this case. D is 2 and log B of A is 3. So 2 is less than 3. So in this case, we're using this case. We basically just plug in this part, which we basically already figured out is 3. And that's how we get n cubed. Okay? So bam, done. Easy. The exact solution, by the way, at some point, I guess I did it, is this. 1001 n cubed. So T of n is equal to 1001 n cubed minus 1000 n squared. This is making an assumption which you typically make. So by the way, I guess I should bring this up. Sometimes you don't get a base case when they give you a recurrence relation like this. And you might be asking yourself, then what is the base case? Like, where is it? Here. What's the base case then? Like, is there a base case? There always has to be a base case. So if you ever run into that situation, just assume that the base cases are going to be T of 0 is equal to 0 and T of 1 is equal to 1. Just kind of go with that. That's usually the case. And so that happens to be the case here too, that we just make that assumption. It doesn't really change anything with that base case being like that because it's relative. Like, what do you consider 1? Like, even in the example from the homework, like, what do we consider to be 1 or 0? And it just means one step, kind of. So, yeah. Okay. So, as you can see, the real solution involved an n squared and whatnot. So it's an oversimplification, but again, 99% of the time, it's good enough. Could we have solved this ourselves using the build and expand method? Yeah, we could have. In fact, you know, I kind of want to, but it's going to take us a while. You know, you could see that, you know, you could very quickly do like one of the steps just to see it. You know, if we were to solve t of n divided by 2, that means this would have been 8 t n squared plus 1000 n squared divided by 2. With the square, you have to do the 2 squared too. Okay, like that. So when we go ahead and plug that in into the top equation, then it turns out that this would be equal to 8, and then the big gap plus 1000 n squared. In that big gap, we have to throw in this whole thing up here. Then I have to shrink it. Why does it keep like sliding down as I shrink it? Like that. Okay? And then we gotta simplify that. So to simplify it, we gotta multiply both sides times 8. So that becomes 8 squared. You can re-magnify that like that. And then this part has to be multiplied times 8 as well. So we'll just make that 8,000. No, actually we won't. We will just leave it as times 8. Okay. Actually, let's simplify the divided by 2 part with the 8, right? Because if we divide by, that's basically by 4. So 8 divided by 4 is 2, right? Yeah, okay. And so already I'm starting to see a little bit of a pattern here, that the general solution is going to be of the form 8 to the I t n divided by 2 to the I plus, and it seems like it's going to be something of the form of 1000 n squared times 8. No, times I. I think it's going to be also times I, but I don't think that's enough because we have a 2 there, and I bet you that 2 is then going to become a 4 and then an 8. So maybe times also 2 to the I. That I'm not 100% sure of, okay? It's going to be somewhere around that. But after you do that, then you can see that this thing could be like before. You can use the logs for that, and so basically come up with the solution. So yeah, if 1000 n squared instead of 1000 n cubed, then would have been n cubed. What do you mean? The final solution, this was n cubed already. 8 times 1000 is 4000. Oh, did I screw that up on the fourth? So well, it was 8 squared. It was 8 divided by 4. So 8 divided by 4 is basically 2. So it's 2000. It's not 4000. I don't see how you're getting. It's a 2 squared. Oh, I see what's happening. You're forgetting that this is squared because we're replacing the n with this term, which means we're replacing n divided by 2 squared, and that squared goes to both the n and the 2. So you're not dividing by 2. You're dividing by 4. So you don't get 4000. You get 2000. So yes. So anyways, once you get that general solution, I'm assuming that I'm wondering how the one on the final solution they got a subtraction. That's the only thing that kind of bothers me, how they got that subtraction part. So because I don't see any negatives being formed here. That's the only part that's kind of weird. Maybe I might have copied that wrong. It might have been a positive. Not sure. But anyways, as you can see, Master Theorem, 1 minute. This version, 1 hour, right? So, yes, Master Theorem is cool. Okay, moving on. Let's see, this one. Oh, this one's the same as the previous one. So that one here, I can just show it to you, but there's no point in writing it out. Actually, this example is this one over here that I have on my notes is basically the same one that we did already, so that one we'll skip. This one's pretty good. Yeah, okay. Yeah, this one, I like this one. I'll do this one. This one is actually interesting because it has one trick to it, and that trick throws everybody off. So that's why I like it. So we got T of n is equal to T 2, 3, n plus 1. Okay? So this one, you got to figure out what A, B, and D are. A can be 1 because you can always add everything times 1 is just the same number, so you can just add a 1 there. No problem there. On the side of the f of n here, what is this going to be? This f of n, you can say that 1 belongs to the class of O constant, right? So what do you do? Well, remember, n to the power of 0 is equal to 1. So you can just go ahead and say n to the power of 0. So then d is equal to 0, okay? And remember, the Master Theorem has limitations on the values that you can have for each thing. But we've run into B. B is a bit of an issue here, okay? What are we going to do with B? B has to be greater than 1. You might be inclined to say that B is equal to 3, right? But is that really correct? Is B equal to 3 in this case, or is it something else? Master Theorem clearly inferior. What should B be equal to? I'll let that simmer. See, my dog is suggesting ideas. 3/2. That is correct. Yes, 3/2. Because what happens if I multiply 2/3 times 3/2? Well, they basically cancel each other out, right? And so what we're trying to do is we are trying to basically put this in the format of n divided by something, right? And right now it's not in that format. Right now it's in the format of 2n divided by 3. So what we need to do is we need to just flip that. It's like a little hack, and make this like that, because then that is the exact same thing as this, but except that this version is okay because now we can actually plug this into our Master Theorem formula. So all I'm doing is playing around with the numbers just so they can fit in the format that I need them to. That's the only hard part of the Master Theorem, is trying to juggle numbers around to put them in the order that it will be okay. Okay? So hopefully remember that basic rule in math, that you take the numerator, put it in the denominator, and if it's a fraction, you just flip it around and you're good to go. Same thing. Okay? So yeah, I have last time I did the class with this example, I guess people were really confused. So I showed them like a super long version of how to do basic fractions. So you can laugh at them for that. I don't even understand how I did so much for so little. But I'm sure you guys understand that. I hope you do, right? You understand how I got this, right? Please. Otherwise, I can show you the super long. In fact, I almost want to show that. I kind of remember this happening, but at the same time, I don't. It's so blurry now, even though it was like a semester ago. But look at all the work that we did to just show that basic thing. It's like, wow, that. Just to show that you can flip the numbers and it's okay. And that's not even the entire thing. There's still like more. this as well. Why does it keep making it like so big? That b is equal to 3/2. Okay, so yes, big log. I don't understand why. I guess somebody see. That's why they require calculus in this class, because then if somebody gives you a question about fractions, you can't be like, I don't know that. But somebody did last time around. So I you know, we had extra time, so I was like, fine, I'll show the whole process of like, I try to make it as simple as possible. I just don't I can't even like understand how I did. But I mean, there's errors involved. I was trying to show them that. So anyways, moving on. Now let's just compute the log b of a. So I already forgot what these were. So we got a is 1, d is 0, and then b is 3/2. So a is 1, b is 0. Wait, no, b is not 0. What? D is 0. Right? So let me make sure I copy that right. Okay, cool. So log b of a. So that's kind of, that actually will require brain power to do, which I choose not to do. Or will it actually? Actually, no, it won't. Because, you know, typically when you have logs, if it's not a whole number, that just makes life not cool. Because then you have to figure out a fraction to what power is equal to this number. And then you gotta, that just requires extra work. But in this case, we're okay. Because the number we're trying to get is 1. And remember, any number that you want, any real number, I suppose, to the power of 0 is going to be equal to 1. So that just, you know, I had a brain freeze for a second, but then I remember that. So we're fine. Okay, so then this is equal to 0 and d is equal to 0. So we have another case 2 scenario where d is equal to the log b of a. So this is no other different than the other ones that we did before. But the tricky part with the b is just to show you that sometimes it might look like it might not work for the Master Theorem, but you can always flip it around and do things to it to make it work. Okay? So in this case, it becomes of the form n d log n. D is basically 0. So that case, it cancels out that term because, again, n to the 0 is 1. So it just becomes actually just log n. Okay? So original equation was this, and already the fact that, see, there was a fraction involved there should have been a sign. Again, there was logarithms involved, and it turned out to be true. But the fact that the d over here, the plus, is 0 means that, like before we had n log n, here we just have the log n. So yes, fun with reciprocals. That's right, that's the name of that. You're right. Forgot what they were called. So yeah. Okay, finally, I think I have one more example. Yeah, this one. For the other case, so we've seen cases 2 and 3. We haven't seen case 1. So here's one example of case 1. At least I think this one will give us case 1. Otherwise, I don't know why I would have it here. So it's t of n is equal to 2t n divided by 2 n squared. So a is equal to 2, b is equal to 2, and then, you know, if you do your in this case, actually, it's just equal to 1, and then it's greater than 1. So this is pretty, hopefully, obvious that d is equal to 2 here. So if you do the log b of a, that's just equal to 1. 2 to the power of 1 is 2. And then you see that d is equal to 2. So 2 is greater than 1. So because of that, we have not seen that case, technically speaking. We have not seen that first case where d was greater than 1 right here. And so the answer to that one is just n to the d. That's it. So I think d is 2, so that means that the answer to this is going to be theta d. Theta n squared. Okay, because n to the d and d is 2. Right? So yeah. Okay, so now changing gears. What does not work? We saw one case, but there's more. So if you look in Wikipedia, there's a couple that don't work. I think it might be just easier to share my screen on that, and we can kind of look at them for a minute. So inadmissible equations. Let's just kind of go over one of each of them and see why they don't work, okay? So looking at the first one, t of n, 2 to the n power, t over n over 2 plus n to the n power. They're really loving the n to the n power thing. So the reason why is a, well, it says here too, that's kind of nice. A is not a constant, right? It's 2 to the n. So a constant means it has to be the same number all the time, like 2, 3, 4, 5, 6, whatever. This is actually not a number that is related to the size of the n. And because of that, it cannot be constrained by the Master Theorem. I can tell you this is probably like some exponential solution anyways, or even factorial. Like, it's just insanely big. The fact, this is the kind of problem that will like never finish before like the universe expires, because of just the n to the n power should tell us that. So I like to get, but I don't think I need the Master Theorem to tell me that that kind of problem would be extremely slow and not useful. But anyways, that is one solution there. Also, d being equal to n is kind of a sign that this would be at least. So even if this whole side of the problem here was okay, if we got rid of this n here, the fact that here the d would be equal to n would show us, case 1, that it would be O of n to the d. So just this part of this would make this be at least O of n to the d. Okay, so exponential. The next one, A is okay and B is okay, but here this is a little more complicated as to the why it doesn't work. It's non-polynomial. You have to understand more about the Master Theorem for this one why it doesn't work. So let's skip that one actually. This one is obvious because A has to be greater than 1, and here it's half, so it doesn't work out. You would think that it would work out. You could even use the Master Theorem in this case, like the formula that I gave you, to still solve it, but the answer would be wrong. So you got to make sure you remember that A has to be greater than 1, and D has to be greater than or equal to 0, and B has to be greater than 1. So I think A and B both have to be greater than 1, and then the only one that can be 0 is D, okay? So, yeah. The next one, f of n, which is the combination time, is not positive. I suppose the fact that here's a negative is complaining it. So I didn't quite say that, but if you saw the formula, on the top of the formula there's a plus. That's important too, I suppose, to point out that yes, you see the plus up there. That means there's no negatives allowed. Okay? And so, yeah, important. Yeah, the rest of them are kind of special and weird, and you have to follow along to understand. This is cool. These are some common algorithms that you might know, or that you will talk about. Like, we will talk about merge sort. But for now, you probably know already binary search. Binary search has the following recurrence relation, and you could actually solve it with Master Theorem. Binary tree traversal we'll talk about later. You can solve it with Master Theorem. You could even solve quicksort, I think, with the Master Theorem. So, yeah. And so, just to kind of give you a taste, there's a lot more to the Master Theorem that I'm talking about. That theta of n part is actually very, very, it's split into like 3 extra cases as well. So, yeah. This is actually a surprisingly, like you said, good article. But in general, it's useful for a lot of practical problems that require recurrence relations, okay? So I thought I'd show it again. It's not technically part of the required material, but I think it's useful to know now. They will talk about it in 477, or probably even in your math classes. So, yep, that's pretty much it. I do have one page at the beginning that I didn't talk about. Runtime of an algorithm on an input of size n is usually denoted as t of n and can be expressed by the recurrence relation. T of n is equal to a t of n. So I guess this is the generic solution. That's why I keep using f of n, I suppose. T of n is equal to a t n over b plus f of n. Okay, so where f of n is the time to create the sub-problems and combine the results in the above procedure. F of n denotes the amount of time taken at the top level of the recurrence. Okay, so yeah. Anyways, thought I'd mention that since I had it written down. Must be important. I can't think of anything else. I mean, I think this is it. This is all there is to that topic, and I'm glad because that's the hardest topic and the one that is less CS. I mean, it's pure CS, but at the same time, it's less data structured. So, yeah. Okay. Well, that is done. Great. Moving on. Let us talk about arrays and linked lists then. So, what are the three main operations that you typically want to do in a data structure? And I have talked about that already, so you probably know them. Take a guess. And of course, they are going to be also applicable to arrays and linked lists because they are data structures. Insert, remove, and retrieve. Yeah, that is pretty much it. You want to insert or store data. You want to access or retrieve the data. And you want to, at some point, delete or remove the data. So let me go ahead and kind of put them here. So you got your insert, your remove, and your retrieve. And so, now that we know asymptotic complexities, why don't we analyze the asymptotic complexities of a linked list and an array, because we know those already. So that's kind of a good starting point to kind of get warmed up with asymptotic complexities. Okay? So, let's talk about inserting. Okay? How long does it take in terms of asymptotic complexity to insert something into an array? And it's almost a bit of a trick question because there's a catch to it. There's a big catch when it comes to inserting data into an array, right? Does anybody have a guess as to what that catch is? And as a hint, it's something that linked list solve. You have to resize the array. That's part of it. Not the entire story, but you're getting to the point. Traversals? No, not quite. That's more of under the access data. We will talk about that, but not for the inserting part. Although it will have to. Okay, traversals do matter with insertion under linked list, but not under arrays, right? So dynamic size. You guys are kind of. You're actually getting part of it. There's two. I should have said there's two tricks to it. One of them is yes. What happens if you try to insert into a full list? Then you got to resize the array. So yes, you guys are correct there. The other side is what happens if you're trying to insert in the middle of the array. Then you gotta move everything to the side to be able to fit it, which means yes, you have to resize again probably, or even if you have space in the array, you have to shift everything forward, right? So yes. So, on one scenario, if all you gotta do is insert at the end of the array and you have space because you made the array bigger than you currently need, which is valid, then I would say that the time it takes to insert is a constant time. If there is space, essentially. On the other hand, as you all have pointed out, if you have to resize, it's gonna take O of n if a resize is potentially required. Now, why O of n? Well, remember, we think of big O as the worst case scenario's upper bound, right? And because of that, the worst case scenario is typically going to be when you got to insert something at the beginning of a list and the array is already full, which means you have to pretty much copy and paste the entire array into another array shifted by one so that you can insert it, right? And because you got to copy the entire array of size n, that means that the time complexity is going to be O of n, right? The best case scenario would be, of course, if there was space, which would be O of 1. All right. So in that case, I would say that the omega would actually be O of 1. And the big O would be O of n. However, it would also be okay to say that the big O is O of 1 as long as you made the assumption that you will always have space available. Okay? So what I'm getting to here is that it's not enough, sometimes it's not enough to just give an asymptotic complexity and give no explanation behind it. Because depending on how you're implementing something, you are correct to give a certain asymptotic complexity if you explain it. Like if you say, my array is always full and it's never going to have space, that is why it's always O of n. Or vice versa. The big O of inserting in an array is going to be O of 1 because I always guarantee you that I'll have space. Okay? So it can be up to debate as long as you explain it. All right, moving on to accessing. Typically, with an array, you can access data immediately because you have an address for each item. So you can just jump directly there to anything, okay? So you can have it O of 1 as long as you're given the index. Now, if you have to search, that's a whole different story, right? If you have to search through the data to figure out if it's even there, it's going to take you longer. How long is it going to take you if you have to search through it? Well, if it's unsorted data, you're going to have to look potentially in the worst case scenario, because again, we care about the worst case scenario. What's the worst case scenario, actually? That's a good question to ask. What's the worst case scenario of you searching for something? Like, imagine that I give you a deck of cards and I tell you, find the heart of the 10 heart, okay? Or find an ace. Find an ace of clubs. I think that's the card, right? Clubs, yeah. What's the worst case scenario? It's not in the list. You are correct. So I pulled the trick on you because it turned out that I actually hit that card. So your deck of cards has every other card except that one. So guess what? You're going to be looking through every single card. You're probably going to check twice because you don't trust yourself. You might think you missed it. Before you're like, yo, this card is missing. And then I'm like, ha ha. Kind of like the Simpson guy. So that is basically the worst case scenario when you're searching, that it is not found. And in that case, the time it's going to take to come to that conclusion is potentially O of n time. So that is in the case of unsorted data. Now, suppose that the data was sorted in an ascending order, okay? How long would it take in the worst case scenario? It's a little bit of a trick question. So how long would it take to search? If I give you again a deck of cards, but this time it's sorted ascending order, so like A's to n time. You guys are correct. It will still take the same time because I'm not taking advantage of the fact that it's sorted. And even if I was, I am looking through the entire list, right? So it's still going to take O of n time. You guys didn't fall for the trap because you might have been like, well, it would have taken less time. Because like once I get past like the 10, I'm like, hey, the card is not here. However, can we do it faster than n time with an array? Can we do it faster? Can we come to the conclusion that the card is not there, which is again is the worst case scenario? Can we? Or can we not? The answer to that is yes, we can. We can use a famous algorithm that I just talked about like 10 minutes ago that was on the Wikipedia thing. Right? When we were looking through the Wikipedia of examples that you can solve with recurrence relation, there was one of them there. It was the first one. It was called, if you go back in the video, binary search. Binary search is how we look through a dictionary. We don't just start from the first page and go all the way to the end. That's horrible. What do? We just kind of pop it open in the middle, see if the letter we're looking at is the first half or the second half, and then kind of split the pages again look there and then split again, and eventually once we get to the last few pages, we're probably just going to go one by one. But we could eventually be splitting half by half exactly, and every time that we're splitting, we're cutting the number of pages that we have to look through in half. And so the half of the half of the half creates a recurrence relation that is something of the form of t of n divided by 2, which at the end of the day is basically log of n time. So yes, we can do better. We can actually find it in log n time in the worst case scenario. Now, for either of these scenarios where it's unsorted or we are using binary search, what will be an example of the best case scenario? What will be our omega? What do you guys think would be the omega in this case? Remember, the omega is the best case scenario. What's the best case scenario if I give you a deck of cards and I tell you to find the card? What's going to be the best case scenario? I should add some cue music, like in my soundboard, like dun 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 dun. 1 of 1. That is correct, except it's not O of 1. It's technically omega of 1. But I know you don't have that probably as an emote. I wish I could add Twitch emotes and add an omega symbol, because we're going to use those pretty often this semester. But yes, omega of 1 indeed. Yes, and what would that actually be like though? Like, tell me what the actual case would be for that omega of 1. Like, that is a correct answer, but the question is, what's the best case scenario for searching a card in a deck of cards I give you? Like, you find it on the first try, yes, which means you literally flip the first card of the deck and it's the card you wanted, like one of those magic tricks where they flip the card and you're like, oh, that's your card. That will be the omega case. So yes, the first item that you look for is that's it. So in the case of the sorted list or unsorted list or whatever, it just happened to be that you got really lucky. That will be the omega. Of course, as computer scientists, we're very pessimist. We're like, oh yeah, that's not ever gonna happen. Or if it's gonna happen, it's gonna be super rare. So we really care about the big O because that's more of the realistic case. But it's always nice to know what the omega is. After all, if everything is all the same, if your big O is the same as everybody else's algorithm, but your omega is better, you can say, technically speaking, your algorithm is slightly better. So, yeah. Anyways, moving on to the remove or delete. The remove or the delete is kind of a trick one, because if you could think of it as a combination of the retrieve, because first you got to find what you want to delete and then you got to delete that. But if we just abstract the fact that we found what we want looking for, and now we just have to delete it, then how long is that going to take? Well, you could in theory say that the omega and the big O of this is both 1. Because technically speaking, if you found the item to delete, we're just simply saying we could mark it as deleted. We don't have to physically remove it. We can just put a flag and say this item is now deleted. It's something that we're going to explore when we're looking at hash tables, actually, of marking things as deleted. For another purpose, but still. And so you might say, and you would be correct to say, that this could take O of n time. If you said, well, as part of deleting, I'm actually going to remove it and shift everything back once. You would be correct to say that it's O of n time. And the omega would be potentially still n time, because even if you delete it at the end or the beginning, you still got to shift everything one way or the other, or maybe copy it to a smaller array. However, if you're just trying to make the deletion super fast, in the best case scenario, you can just mark things as deleted. Which, by the way, I think vectors play that game, but I'm not 100% sure. Okay, so that's arrays. We are running low on time to talk about the linked list side of things. So maybe let's just talk about the insertion of the linked list, okay? So, how does the insertion work with linked list? Linked lists have the beauty and power that you can just insert anywhere you want by just fiddling around with pointers and make things immediate, right? But there's a catch. You don't have direct access to every element in the linked list like you do with arrays. You have to traverse the list, as you guys said earlier. So it turns out that the omega for inserting could be the same as the big O, which would be n, if you have to actually traverse the list to the spot where you want to insert. Suppose you have a pointer at the beginning, at the end of the linked list. the worst case scenario is still going to be the one right before the end, because you still got to traverse the whole list all the way to the end, right? Or in the middle, in the case that it's a doubly linked list and you can go in both directions, right? In which case, the middle would be basically just n divided by 2, but that's just a constant, so it's just n at the end of the day. So I'll talk more about that next time, but I just wanted to start introducing you to actually applying asymptotic complexities to stuff that you already know, because that's what we're going to be doing with algorithms that we learn. So we have to start thinking of that sort of analytical way. Okay? So for the next assignment you're going to get, I want you to practice coding in linked lists, because I'm required to give you a linked list assignment. So you are going to be taking your first assignment and you're going to be converting it into a linked list as part of the assignment. So the list of ships, you're going to make it to a linked list. So I'll be posting that within the next day or so that you guys can get going on that. So that'll be a bit interesting. So yes, that's it. That's all I have for you. So today we talked about the Master Theorem, a little bit about analyzing asymptotic complexities, and like I said, I have definitely not given you the full story of the Master Theorem, but I think I've given you enough that you can actually use it for some rather practical purposes. When will the assignment be due? The next assignment, the linked list one, probably within the week. So probably like next Sunday, not this Sunday, but the Sunday after that, something around then. Since I mean, it's linked list related, but you guys know linked list from 202, so yeah. Cool. Well, I know it's Wednesday, but it's kind of like the end of the week since I don't see you guys until next week. So I hope you guys have a good weekend and a good rest of your week as well. Hope you learned a lot, and until next time. His name is John C. See you guys. Toxic. I can't even hear it, but I saw the icon, so I have to watch I'll have to watch the replay to see it play. But all right, see you guys later. Feel kind of sad you got scammed out of what, like 25 cents or whatever that was, but oh well.